We are now recording. So you say you have no questions, issues, or concerns, right? Yeah. Okay. Well, where we left off last time, I'll go back to the book. We're doing separable equations, and this is an illustration of how we could conceivably. I got to scoot you over to the right a little bit. In fact, I don't think that's going to work well, so I'm going to move you to the top. There we go. Okay. Here is example 3. Here's an equation. Solve this differential equation. dy dx is equal to y squared minus 4. Okay. Looks like a pretty straightforward one. So let's go to our whiteboard and work on it there. And if I can find my pen in the Wacom tablet, dy dx is equal to, here we go again, not writing well, y squared minus 4. Now, if you remember back in 2.1, we would have called this an autonomous differential equation because there aren't any of the independent variables x, and why did that right there, I don't know. Let me see if I can get that to erase. I can't seem to get my eraser to connect. It will not open. And I don't know why. There. Try it again. Well, it looks like I'm not going to be able to erase. Sorry about that. I don't know why. This is sort of it's a Wacom problem, I think. I don't believe it's maybe how it interacts with Zoom or interacts with I don't know. I just don't know. The eraser is not working. But when we were talking about this before, we called this a autonomous differential equation, and when we were talking about it, we would have said that it has critical points. Oh, is there someone coming in? Yes, James is here. Let me get James here. Welcome, James. Sorry, I don't want to drop this stuff, but I'm having trouble getting my pen to write in my gradebook. There, we got it. James is here. Okay. Now come back. Okay. We would have said, without being able to solve it, just sort of describing it, we would have said, I don't know why all my wires are getting tangled up. We would have said that y is equal to plus or minus 2 would have been equilibrium points, critical values. We would have given it some name like that because that's where your first derivative would have been 0. Not on x's, but on y's. Y is equal to plus 2, minus 2, or plus 2. Okay, all the curves would have been going in those directions. Let's see if I maybe can get the eraser to show up again. Nope, it just is not functioning. Okay. Well, now we're going to try to solve this system of equations. Before we couldn't solve it, we could just say what it looked like. Okay, we called them solution curves without a solution. We just didn't know what the solutions were. Now let's see if we can do it. Well, these are certainly separable because there is no x here. Okay, so we can write that in differential form. That would be dy is equal to y squared minus 4 dx. Okay, then divide both sides by y squared minus 4 and this would have been gone to 1. Okay, and then how to solve this one? Well, I would have solved that using partial fractions and done 1 over y squared minus 4, which I would factor as y plus 2 times y minus 2. It's pretty ugly. Is equal to some a over y plus 2 plus b over y minus 2. Multiply both sides of the equation by the product, least common denominator, y plus 2 times y minus 2. The pen's not writing well, sorry. Y plus 2 times y minus 2. Multiply this one by y plus 2 times y minus minus minus. This is so aggravating too. Okay, now here denominator, which is that, disappears and you just have left on the left hand side 1. Now here y plus 2 and y plus 2 divide out and you're left with a times y minus 2. We'll just leave it like that for now. Plus, and here the y minus 2's, whoops, wrong one, go out, and left with b times y plus 2. Okay? Now, oh, here comes Kira. Good deal. Let me get her here. Let me get her marked on the roll, and I'll be back in just a second. Okay, because this pen is not doing well. Okay, got Kira here. Okay, we've got 3 so far. Okay, let me just make sure that no one else has snuck up while I wasn't looking. Yep, 3 students and me. Okay. Now, if you remember your partial fractions, this equation should be good for any values for y. So let's just let y equal 2. And what you would have then is 1, because there's no y over here. This would go to 0, and that would be equal to 4b, which of course would imply that b is equal to 1/4. And we'll let y equal negative 2. This is y equal 2. When y is equal to negative 2, you'd have 1, because there is no y over here, is equal to, and this would be a minus 4a, and this would go to 0 then. So this would imply that a is equal to negative 4. Negative 1/4, sorry. Okay, now, so this equation here, that integral here, and we're going to integrate this as well. Okay, this one would be the same as the integral of, I'm going to put the b in. Oh, here comes Ryan. Now I can't let him in because Miguel, you're in the way. Okay, there he is. Now I've got them in. Okay, I'll move you back in a bit. Okay. Ryan is here. Okay, so we're just missing Jemanuel. He was here in the first class, but he's not here yet in this class. Okay, now, there's my pen. All right. Now, this Wacom also has a keypad on it that sometimes clicks and sometimes doesn't. Okay, I'm going to rearrange these and put the B one in front because it's positive and the A one's at the end. So this will be 1/4. Since both of them have 1/4 on it, I'm going to put the parentheses there and have 1 over y plus 2 dy minus the integral, because 1/4 is out front, I'm going to put the dy on top, dy over y. Now I got those backwards, didn't I? This is the minus, this is the plus. And as far as I know, I can't get my pen, my eraser to do. So this is a minus here. That's a minus. Okay. Because the B was minus and it's plus. Okay. All right. So this is the left-hand side. The right-hand side is just the integral of dx. So that's just going to be x. I know that one's going to be true. So what do we have here? 1/4. And this will be the log of absolute value y minus 2 minus the natural log of y. That's a 2. I don't know how it became a 1. Goodness gracious, the old gray cells, they ain't working well today. Y plus 2. Okay. And this is equal to x. Okay. So first thing I'm going to do is multiply both sides by 4. Okay. So this gives us the log. I'm going to do something else at the same time. Y minus 2 over y plus 2. Because when you have a difference of log, that's the log of the quotient, is equal to 4x. Okay. Now, what this does, we need to do, and we need to put a plus c out here somewhere, but I don't know what form to put it in. I guess we'll just put it as a c. We're going to fiddle with it later. We're going to take the e of both sides, and this just gives us y minus 2 over y plus 2 is equal to e to the this thing, okay, which is the same as some other c, e to the 4x, okay, because the e to the product, a sum is the product of e to the c times e to the 4x. E to the c is just some constant. So that's a different c from that one, but just some constant. Okay? And then the last thing, well, I don't know if it's the last thing we're going to do. And they actually do call it a plus or a minus. Okay. They okay. here's where they kind of go off track here, and what they do is perfectly legal, but they just skip too many steps getting there. So here's what I'm going to do. I can't erase. That's the big problem here. So let's write this as y minus 2 is equal to y plus 2 times c e to the 4x. Okay? And then write this as y cy e to the 4x plus 2 c e to the 4x. Okay, just multiplying, distributing that across, and then add 2 to both sides. Okay, so this is going to be a plus 2, and we'll lose it here. So this is what y is equal to. I'm sorry, I'm just running incredibly out of room. And they actually have, I'm sorry about this, but I guess we need to do it. This should have been plus or minus e to the 4x plus c2. Right here, I can't get my pen to show up. There it is. This should have been a plus or minus, and the reason for that is the absolute value bars. There should have been these. I dropped them because I just was tired of writing them. Can't find. Oh, there it is. Okay, this was absolute value. This was absolute value, and then to remove the bars, that means it's either going to be plus or minus. So that's where your plus or minus came from. Now, this is either now a plus or a minus of this. So what they do, and I don't have enough room to do it, so I'm just going to take you back to the book and show you what it turns out to be. They're not as interested in what the answer is what form the answer has. So let's go back to the book, and there it is. Okay, so you see we started out the same way they did. They got this, and sure enough they did the integration, partial fraction integration, got the same thing we did. Now the second equation is a result, and I'm going to have to move Miguel out of the way again. There we go. Okay. This is, you got from partial fractions like we did on the left hand side of the first equation. Integrating and using the rules of logarithms gives you, well, the integration gives you this, okay, and that's equal to x plus c1. Now they're going to call it c1, I just call it c, okay. And then the multiply both sides by 4, and that gives you a c2 then, because 4 times c1 is still a constant, so they call it c2. But there's absolute value here, so when you do take the exponential of both sides, and lose the absolute value, that gives you the plus or minus here. Okay, and that's what I was trying to show you before, but I just ran out of room to write it. Now, what they're skipping now is how they get from here to here. Okay, now I wish I had room to write it, but you can do multiply both sides by y plus 2, and when you add that or subtract that, okay, that is going to ultimately come up with a plus up here or a minus down here. Okay, now that wasn't very satisfying of how I'm saying it, but I just don't have room to work it out. I guess we could go to a whole new page and do it, but that would just take a lot of time. If we factor the right-hand side of that differential equation, okay, which was here, the original differential equation, this is y squared minus 4, right? We know from the discussion of critical points that y is equal to 2 and y is equal to minus 2 are two constant equilibrium solutions, which I mentioned before, if it's treated as an autonomous differential equation. The solution y is equal to 2 is a member of the family of solutions defined here. When you set x equals 0, would that work? E to the 0 is 1, that's 1 minus c. Not sure that would be a particularly good choice. Yeah, well, when y is equal to 2, that means it says for value c is equal to 0. Yeah, that works. When c is equal to 0, y is equal to 2. That works. Because if this c is 0 and that c is 0, they're the same c's, then these two are both 0, and you have 2 over 1, which is 2. So that certainly works. However, y is equal to negative 2 is a singular solution because you cannot come up with a c that would give you that solution. Okay? No matter how you try to do that, you cannot get this thing to turn out to be a minus 1. Okay? So that solution, y is equal to negative 2, doesn't show up here at all in your family of solutions. That makes it singular, but there's no way you would see it from this solution set. Okay? Or this solution, yeah. Just no way that y would ever be negative 2. And yet we know it has to be. So that makes it our procedure then lost it. And I'll show you exactly where it lost it. Right here. Okay, well, not quite. When you divided both sides of the equation by y squared minus 4. That can never equal to 0. Okay? Now, they got by with y is equal to 2. That produced a solution, thank goodness, but y is equal to minus 2 would not produce a solution because in that case it just failed to work. So you have to be wary anytime you divide to separate your variables. Dividing by this puts in jeopardy y is equal to plus 2 or y is equal to minus 2 as potential solutions. Because dy dx is equal to 0, that's a perfectly legitimate thing. Your slope is 0, and we know it is at minus 2 and plus 2. But we can find the plus 2, surprisingly, from this solution, but we cannot find the minus 2 ever from this solution. So that singular solution is lost when we do this. So And we say lost because it didn't show up in our family of solutions. Okay. Now, how to watch that? Notice that you can't divide. Now, by the way, here's another way. Once you get this form, log of this, certainly y equal minus 2 is not going to work at all, because that would be the log of an infinitely large number, or approaching 0, and that doesn't exist. So that's the other reason. The y equal 2, it sort of sneaks by because that's okay. That's not an indeterminate form here, but y is equal to minus 2 is definitely not okay. Okay? Definitely not okay. All right. Now, let's move on to example 4. Okay. I think what I'll do is go back to the whiteboard here, and we'll work this one out. If I can get this to show up. Okay. Now, we still got, yeah, we got 4 students. We're only missing Jemanuel. Okay. So let me, first thing I'll clear the scratch off the board, and then I think I'll move Ryan down here this way. Okay, you can't see that, but now let me get my Wacom pad and my stylus, and we're doing example 4, an initial value problem. Here is the differential equation. Open parentheses, e to the 2y minus y, that's down on the lower level, cosine x dy dx is equal to e to the y sine of 2x. All right, that's the differential equation. Here's the initial value, y of 0. Get out of there. Sorry, I don't know if you can see that, but my screen kind of messed up. Y at 0 is equal to 0. Okay. I hope I've copied the problem right now. Excuse me, just a minute. I ate the first part of my lunch way too fast this morning, and I have not felt well since, so hold on a minute. Okay. I hope that'll sort of settle my stomach a little bit, but no guarantees. Okay. Now, this term here is all a function of y. That one's all a function of x. Here's a dy dx. We can write that in differential form. This is a function of y alone. That's a function of x alone. Yes, this does look separable. So the first thing I'm going to do is write this as e to the 2y minus y cosine x dy, writing this in differential form, is equal to e to the y sine of 2x, sorry, don't make that mistake, dx. Okay, now we want all the y's over there to the left with the y, all the x's over here to the right with the x. So what we're going to do is divide both sides by cosine x. And also divide both sides by e to the y. Okay. Trying to think where the best place to put it. Probably here will be good. Okay. So the cosine x's go out here. The e to the y's go out here. And now what we have left, and I'm going to call on a few situations here. First, I'm going to write this as e to the 2y over e to the y minus y over e to the y. Okay, I think you'll see why in just a minute. It's e to the 2y over e to the y minus y. Here we go again. Over e to the y. Okay, that's times dy is equal to, now I'm going to call on a trig substitution here, trig identity. Sine of 2x is twice the sine of x times the cosine of x. This is 2 sine x cosine x. Okay, that's a pretty ugly looking x dx over cosine x. All right, now here, sorry, this is not getting any better. It feels like it's getting worse. Let me get water and see if that'll help. Okay, now e to the 2y over e to the y, anytime you have same bases, different exponents, and you're dividing same base, different exponents, keep the base, subtract the exponents. That's e to the 2y minus y. That would be e to the y. So this one becomes e to the y minus, now I'm going to rewrite this as y e to the minus y. I don't like having my variable in the denominator. So this is the left-hand side times dy is equal to, now over here, one of the cosines go out, and that just simply leaves you 2 sine x dx. All right, we can, and hopefully will, integrate. Goodness gracious, that's so bizarre. Just writes wherever it wants to. Sometimes won't write at all, other times writes just wherever it gets a notion to. Okay, now I can integrate the e to the y. That is e to the y. If I can find my pen, there it is. E to the y. Now this one's, oh, I'm so sorry. It's going to need an integration by parts. So let's go up to the top and do that one. Minus y e to the minus y dy. And I'm going to integrate that. Okay. Integration by parts says take the one that's going to get simpler when you take a derivative, and the one that isn't going to change much when you take the integral. So that's going to then let u, I said it that way, let u equal y, and I'll just write it that way since I already started on it, and dv is equal to e to the minus y dy. The d's always go with the d's. Okay, this will then produce du, I'll say it, write it the right way, is equal to dy, and over here v is equal to minus e to the minus y dy. See, that didn't get any worse integrating it. Okay, now what does that give you? Remember, you do have this minus sign out front. Okay, so this integral will now be uv, which is this times that. With that minus sign, that's going to be plus. So that's going to be y times e to the minus y. Okay, there's not a dy here. dy is with the d. This is just e to the minus y. You don't ever do a plus c there. I don't know why I wrote down dy. Okay? Now, minus, and you have a minus here, a minus that comes from here, and a minus that comes from there. There's three of them, so that's don't leave it a minus. The integral of the bottom line here, okay, and that is e to the minus y dy. That's this dy comes down here. Okay, that will give us y e to the minus y okay, there's too many moving parts here. The integral of e to the minus y dy is minus e to the minus y dy. You have a minus out in front, so those two minuses become a plus. If I could get my pen ever to show back up again. Where in the world is it? There it is. Okay, so that's going to be plus e to the minus y. Okay, now after this one we can put our plus c. Okay, well, it doesn't matter. We're going to put it on the other side. Okay, when we do this one. So this was the e to the y that we had there, and then this will be plus y e to the minus y plus e to the minus y is equal to, antiderivative of sine is minus cosine, so this will be minus 2 times the cosine of x. Now we can put our plus c. Excuse me. Now, our initial condition that y of 0 is equal to 0, it means for x equals 0, y is equal to 0. So that gives us, if I could get the pen to show back up, where are you, pen? Here you are. E to the 0 is 1, plus 0 times e to the 1 is still 0, plus this will be, when y is equal to 0, e to the minus 0, be 1 over e to the y, 1 over e to the 0. E to the 0 is 1, so that's just going to be another. So the left-hand side adds to be 2. The right-hand side, if I could get my pen ever to show back up, where is, there it is, okay, is equal to, when x is 0, cosine is 1, so that's a minus 2 plus c. Well, add 2 to both sides, you get 1 plus 1 is 2, plus 2 is 4, so c is equal to 4. Okay? Now, your final answer is this, e to the y plus y e to the minus y plus e to the minus y is equal to of minus 2 cosine x plus 4, because that was your C. So I think that's the answer. Now, number one, this is a very ugly looking y. Okay. Frankly, I can't think of any way to make that look better. Maybe if you factored out an e to the minus y, this would jump up and become e to the 2y plus y plus 1. You know, I don't know. I don't see that gains you much. Let's see what they got. Okay, e to the y okay, where in the world there's my pen. I don't know, it just sort of disappears sometime, and there it is. There it is. So e to the y plus y e to the minus y plus e to the minus y is equal to, and they put the 4 first, 4 minus 2 cosine x. Yep, that's exactly what we got. Now, is there any chance of being a lost solution in there? I don't really think so, because, well, you always have some possibilities. You divided both sides by e to the y. E to the y is never 0. No sweat there. You did also divide by cosine x, and cosine x is 0 at all your half pi's. Okay, so obviously your half pi's are out of the question here. Now I'm going back to the book just because I don't want to draw those scales. Okay, here we go. Still just 4 people here. Okay. Now, here is a representative sampling of those curves. That's for various values of C. Okay. We had the initial condition implied for us that C was equal to 4, but goodness gracious, my cords are getting all tangled up. When C is equal to, well, we know that x equals 0, y is equal to 0. That's the curve right there, because that's the only one that passes through the origin. Okay, the rest of these, that would be a plus numbers. These would be minus numbers. This is the only one they show that would pass through the origin. Okay. Now, goodness gracious, I just feel so rotten. Okay, this is the one where C is equal to 4 then. That is the curve we were talking about. They've now colored it blue. The next one down here happened to be where C is equal to 2. That wasn't what we had here. That wasn't the value you got down here. So that's why they drew it. I don't know. Now I've got to move James out of the way a little bit here. Okay. They do mention use of computers, and they also mention this in the remarks at the end of the section back at 1.1. Way back there. And I'm not sure. Oh, I don't know why they picked this one out. This one down here was when y at when x equal pi halves, y is also 0. Pi halves is what? 1.57, about 1.57, okay? And that would be something around there. There's 1, there's 1.5, this is a little bit to the right of there, and there we know that the y is equal to 0. Well, this curve up here, this family of curves, which is one that gives you that. Okay. All right. Don't know why they picked that one out, but they did. And that would indeed be the curve with that initial value. This would then be the curve, because that's the one, I guess it's this one right here. Okay. Now, let's see what other strange and unusual things they did here. Is that someone coming in? I don't think so. Let me just check. Wait, that's not what I want. That. Nope, we still got the same. Well, actually, we lost it. Yeah, we had 4. 1, 2, 3, 4. Yeah, that's right. Okay. Okay. Let's proceed downward here. If an initial condition leads to a particular solution by yielding a specific value of the parameter c, like we just did in a family of solutions for a first-order differential equation, there is a natural inclination for most students and instructors to relax and be content. However, a solution of initial value problem may not be unique. I was trying to think of sort of a typical example of that. A couple flashed through my head, but I don't think they are all that useful, so let's just go on. We saw in example 4 of 1.2 a while back that the initial value problem for this one, when y is equal to 0, has at least 2 solutions. Y is equal to 0 and y is equal to 1/16 x to the 4th. We're now in a position to solve the equation, so we're going to solve this one. So let me get my I'll tell you. Okay. All right. Let's go back to the white screen, whiteboard. All right. Let's get Ryan out of the way here. Okay. Clear previous drawings, and this is going to be this one. It's not one of the examples in the book, but it's one that we have talked about before. Excuse me. dy dx is equal to xy to the 1/2. Remember, they kept giving us solutions saying verify and that kind of stuff, but we weren't ever able to get them ourselves. And we have an initial condition that y at 0 is going to be equal to 0, I think. Yeah. Now, and we'll see why we come up with 2 solutions, even with 1 initial value. Okay, this is separable. First thing we'll do is write it as a differential rather than a derivative. That'd be dy is equal to x y to the 1/2 dx. Okay, writing it as differential. Let's divide both sides by y to the 1/2. Okay, Over here they go out, and here I would rewrite this as y to the minus 1/2 dy is equal to x dx. Okay, now we're ready to integrate both sides. Now, my tendency is to say, okay, what have we just done that could have created an issue? Wait just a second. Well, we divided both sides by y to the 1/2, but when y is equal to 0, you can't divide by y to the 1/2. So this step right here, if I could just get my pen to show up. Where is it? There it is. Okay. But it's still not moving. Now, why isn't the pen moving? It's doing all sorts of weird things. See, the pen is sitting right there somewhere, but I cannot get it to write. Now, earlier the eraser quit, and now the pen has quit. So this is really a pain in the neck. Well, I'll move it this way. Okay. When we divided both sides by y to the 1/2 here, we were basically dividing by 0 for this solution. So that's not a fair thing to do. Okay. So no wonder we came up with multiple solutions, because we can't divide by 0. Okay. So everything we're going to do from this point on can be suspicious, because we got here by dividing by 0, which is not very fun to do. But let's do it if we can. Integrate y to the minus 1/2, and still this isn't working. Okay. I cannot get no matter. Oh, I was using the wrong side of the pen. Sorry. Okay, integrate this, and that be y to the, add 1 to that, to the 1/2, divide by 1/2, which is the same as multiplying by 2, is equal to x squared, 1/2 x squared, plus c. Again, increase this by 1, that'll be a 2 divided by 2. Okay, now I don't really want that to be my c. Here's what I want it to be. 2y to the 1/2 is equal to x squared plus c. That's really a 4. And that's the c. Goodness gracious, I said c and wrote y. I can't get my pen to erase. Let me see if I can now. Nope, still won't erase. Okay. So if we solve this for y, I guess we really wanted the 4 over there, or we can square both sides. This will be 16y is equal to x to the 4th plus c, x, let's see, x squared plus c squared, I think is how they'll do it, and then divide both sides by 16. Alright, let's see if that's what they got. Yeah. Okay. And I think we'll just stop there and go back to the board, because I'm running out of room and I can't erase. Okay. Go back to the book is what I meant to say. Now I've got to move James out of the way. James, you're in the way again. There we go. Now, here was the problem we were just working with that initial. Oh, I forgot to solve for that. Sorry. Let's go back and do that. I meant to solve for it. Okay, Kira, move back down. Okay, let's go back to that. I didn't want to solve for that. Okay. And now, why did all this move? This is so aggravating. All this had been properly in place all that time, and now I have to move it again. Okay. Okay, but that's still positioned well. Okay. We divided by 16. So what we wound up with, y is equal to x squared plus c squared over 16. Now let's plug in 0, 0. So the y is going to be 0 when x is 0, and that's going to be when c, and that's a 2 there. I don't know why it looks so much like a 3. The pen is dragging, equals c squared over 16. Okay. Now, so c is equal to 0. I was going to say that's what I got. C is equal to 0. Okay, so what we have then is y is equal to x squared over 16, x to the 4th over 16, because it's x squared when c is equal to 0. That's one solution, and sure enough, when x equals 0, y is equal to 0. That works. But we also know that when you could just have the equation y is equal to 0. Now that certainly, it does happen when x equals 0, but this is x to the 4th, so they have the same initial value, but there are two different functions there. This is a quartic function that, if I can draw it, it comes down pretty sharply, hangs around here, and then goes back up fairly sharply. I don't have enough hang time down here. It's more like that, sort of flat, and then moves up. Or this function here, just y is equal to 0. Both of those are solutions. Why? Because we lost this one when we divided by 0, which isn't a very fair thing to do. Now, let's go back then to the book. And now I've got to move you again. James, you're in the way again. There we go. All right. That was the solution we got because c was equal to 0. Y is equal to this. But here was the other solution we didn't get because this one had y values other than 0 anywhere other than x equals 0. This has y values equal to 0 everywhere. Now in position to solve the equation, separating the variables. Oh, I'm sorry, we've just done this. We did all this. I'm sorry. This is what we got. And we see that x equals 0, y is equal to 0. We see that c is equal to 0. We've done that. Therefore, y is equal to 1/16 x to the 4th is a solution for that initial value problem. The trivial solution, y is equal to 0, was lost because when we divided by y to the 1/2, we were dividing by 0. So it actually possesses many more solutions, since for any choice of parameter a, you can have x minus a squared squared here, not just x minus c squared. So it satisfies both the differential equation and the initial condition. Said see this figure. Well, here's what the illustration of that is. Y is equal to 0, of course, would be the x-axis. That's the trivial solution. Okay? And that's good for any x less than a. For any x greater than a, then this is the solution. That's that quartic solution right there. But for any x greater than a, you can then move that to the right a square units, and you still have that solution. Okay? So it solves the differential equation and the initial value problem. Okay. Now, the next thing they're going to talk about here is a really difficult, well, not difficult, it's hard to deal with. Let me put it that way. Integral defined function. And we talked about these, I think they said back in section 1.1. It's pointed out that a solution method for certain kind of differential equation may lead to an integral you cannot solve. You cannot integrate. That is especially true for separable differential equations, because integration is the method of solution. So for example, if g is continuous on some interval I containing x0 and x, then a solution of a initial value problem, dy dx equal g of x, where y of x0 would be y0, is defined this way. Write that in differential form. Dy is equal to g of x dx. Integrate that, you get y of x is equal to the integral from well, basically an indefinite integral of g of t dt. Okay, you can still call it g of x dx, but the next step you're going to do, and then plus c, but when x equal x0, this is equal to y0. Well, when x is equal to x0, this goes to 0, so this thing would have to be y0 here. So there is your plus c. And the only way to get this to go disappear is for your x to equal x0, so then this leaves you with an integral defined function. Now, if you can integrate the g of t, fine, do it, you know. But if you can't, this is an integral defined integral defined solution. Okay. And if that's non-elementary, meaning there is no solution for that, it cannot be expressed in terms of elementary functions, then that is your best solution. Okay. How do you deal with it? Numerical integration. Okay. About the only way you can in a practical sense. Now, how are we doing? We've got a little time left. Let's see about example 5 here. Yeah. Let's go to our white page and do what we can on it. I'm not sure we'll be able to finish it because it looks simple enough, but it's going to be somewhat of a pain. So let me get Kira to move down here a little bit again. Clear the screen here of all drawings and find my pen and do it. Here's the differential equation. Dy dx is equal to e to the minus x squared. Hope some of you are cringing right there. Okay. Initial value, y at 3 is equal to 5. Doesn't look like much of an initial condition, but it's a fixed condition. Okay. Rewrite this in differential form and make it dy is equal to e to the minus x squared dx and integrate both sides, and this will be y is equal to that integral, whatever that is. I can't integrate that, and I bet you can't either. E to the minus x squared dx plus c. That's all we can leave it as there. But we can plug in when x is equal to 3, y is equal to 5. So this will be 5 is equal to, and we'll do what they did before. We'll put this as 3 to x e to the minus t squared dt, just using a dummy variable there, plus c. And for this, okay, when x is equal to 3, this integral goes to 0, and that leaves your y is equal to 5. So this makes this, well, I shouldn't have written it there. I should have left it the way it was. So our solution is y is equal to, and they usually write this first, I don't know why, plus the integral from 3 to x of e to the minus t squared dt. And that, by the way, is how you have to leave it. There's just no other way to express it. And that, I think, takes us to the end of the section. So let's see. Okay, let me move James again. All of you, actually. Okay, so here's the problem. That's what we're trying to solve. Step through it just like we did. And the y of 3 is equal to 5, so that gave us y of x is equal to 5 plus that integral, 0 to x e to the minus t squared dt. The procedure demonstrated here works equally well on separable equations, g of x times f of y, where, say, f of y produces elementary derivative, but g of x does not. So then you would have just the right hand side, the x side being an integral, the y you can calculate. Now here are the remarks. Usually I don't do much on those, and I don't think I will this time either. I don't see anything special here. So here's the homework exercises. Do any of the odds 1 through 21. Okay, you see them all there. Any of the odds that are in the back of the book, 1 through 21. Then do any of the odds 23 through 27. Then do 29, if that's in the back of the book. See if you can do that one. And then 31 or 33, whichever you'd like. If they're in the back of the book, do them. Then 35, any of the odds 35, 37, I think it goes down to 39. No, 35 or 37 if those are in the back of the book. And then do any of the odds 39 to 41 if they're in the back of the book. And let's see, that gets us through 41. I think 43 is up. No, it isn't. Okay, I thought 43 was up there, but it's not. It starts down here. There's 43. If that's in the back of the book, do that one, and then you go back up here and do any of the odds 45 to 47. Okay, if they're in the back of the book, do them. Usually the discussion problems are not in the back of the book, so you don't have to worry with those unless you find one that is, and then you may want to work through it using the back of the book as a help. Computer lab assignments. I don't have a computer lab. If you have access to one, you certainly can try it. There's a mathematical model here, suspension bridge, and that basically is a tautochrome or bakustrochrome. I can't remember which. But that's the way you solve those. All right. I think That finishes that, and we're ready for linear equations. How are we doing on time? Look at that. It just turned 3:45. So that's it for class today. We'll be starting 2.3 next time, and we'll be dealing with linear equations. Okay? Now that was a whole class of differential equations, but now we're dealing with first order linear equations. Now some of these linear equations may be solvable by separation of variables. If so, we can check them that way. But we're going to go through and treat these, especially those who aren't separable. We're going to develop a technique to solve any linear equation, and then we'll compare that with the ones that we can do separable. All right, so we'll pick up and go from there next time. Any questions, issues, concerns, problems? All right. Well, then if there are no questions, I'm going to stop the sharing right here. And I'm tired of sharing. And then I'll end the recording. If there are no questions, are there any final questions? All right, I'll see some of you tomorrow. I think the two that are left, one that we lost, and we'll see you tomorrow for linear algebra. Okay, take care and be safe. Bye-bye.